This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on U-substitution with definite integrals. Our first example is the integral from 0 to 1 of x times x squared plus 4 to the third power dx. We need to define our u. U is the thing whose derivative shows up in some version later. The derivative of x squared plus 4 is 2x, and that is some multiple of x. Therefore, that's our choice for u. U is often in parentheses or in the denominator. You'll see some examples on how that's going to work. So we're going to let u equal x squared plus 4. Taking the derivative with respect to x of both sides, the derivative with respect to x of u is the derivative with respect to x of x squared plus 4. The right-hand side, of course, is 2x, but the derivative with respect to x of u is du dx. So we get du dx is 2x. My strategy requires you to solve for dx. So if du dx is 2x, du is 2x dx. And we can divide by 2x to say that du divided by 2x is dx. That is going to replace that value for dx. That will be du over 2x. X squared plus 4 will be u, and x is going to cancel. But we have to manage the endpoints. This is an x of 0, and this is an x of 1. We need to do the integral in u, so we're going to change those. So again, just to clarify, that integral is x goes to 0 to x goes to 1 of that function. Now, if x is 0, what is u? We plug 0 in for x and get 0 squared plus 4. So if that's the case, 0 squared plus 4, we get u is 4. So my starting point here where x is 0, I'm going to rewrite as u is 4. Now if x is 1, again, u is x squared plus 4. Plugging in the 1, we're going to get u is 1 squared plus 4, or 5. So u is 4 in the lower endpoint, u is 5 at the upper endpoint. U is x squared plus 4, and du divided by 2x is dx. That gives us enough to make all the substitutions, and hopefully we'll have an integral that is just in u. So indeed, starting point, u is 4, ending point, u is 5. X is here, x squared plus 4 is u to the third power, and then du divided by 2x. The good news here is all of the x's go away. This x cancels that x. This 2 downstairs, you can think of a 1 being upstairs, we can perceive as a 1/2, and that will come out in front of the integral sign. So from this then, pulling out the 1/2, we have the integral of 1/2 u from 4 to 5 of u to the third du. To do the integral of u to the third, we think power rule. Integral of x to the n is x to the n plus 1 over n plus 1. So the integral of u to the third is u to the fourth over 4. Now we're evaluating this as u goes from 4 to 5. But 1 over 2 times 1 over 4 will be an eighth. We can simplify this, take this 1/8 out, and then we have u to the fourth evaluated as u goes from 4 to 5. Plugging in the 5 first, 1/8, 5 to the fourth, minus plugging in the other number, 4 to the fourth. And that, of course, is in parentheses. So the arithmetic, 1/8 of 625 minus 256, and we get an answer of 369 over 8. Our next example is the integral from 0 to 2 of 5x over x squared plus 9 dx. Our u is going to be x squared plus 9 because his derivative is 2x, which is a multiple up here of 5x. If the derivative has its multiple somewhere else so that it will cancel somewhere else, namely in the numerator, then we're going to have a good chance to have our u substitution strategy work. So again, u is x squared plus 9. The derivative with respect to x of u is the same as the derivative with respect to x of x squared plus 9. So du dx is 2x, and with my strategy, we're going to solve for dx. If that's the case, du will be 2x dx, and then dividing by 2x, du divided by 2x will equal dx. That's that substitution. X squared plus 9 will be u. And then the last thing we've got to work on are the endpoints. Starting endpoint is 0, upper endpoint is 2. But those are x's. Those endpoints represent x's. I want to convert those to u's. So we'll plug 0 in for x. 0 squared plus 9 will be 0. Plug 2 in for x. 2 squared plus 9 will be 13. 0 squared plus 9 is my lower endpoint. 2 squared plus 9 is my upper endpoint. 5x over, there's your value u, because u is x squared plus 9. And dx has been substituted with du divided by 2x. So now, what do we have? U runs from 9 to 13, changing the endpoints. The x's cancel, which we want to happen. We just want to have u's. So 5 over u times du over 2. And of course, that 5/2 will come out in front. So we have integral as u goes from 9 to 13 of 5 over u times du over 2. 5/2 is multiplied in there. That's going to come out. Integral from u to 19 of 1 over u du. And then we have to remember the derivative of natural log of x is 1 over x. So the integral of 1 over x is natural log x, actually natural log absolute value of x. So the integral of 1 over u is natural log u. So we have 5/2 natural log absolute value of u as u ranges from 9 to 13. So it'll be 5/2 times log 13 minus log 9, where log 13 and log 9 are in parentheses. And that's that problem. Next up, we have the integral from 1 to 3 of log x over x dx. It's not obvious what the u would be here. U is log x. Its derivative is 1 over x. Do we see 1 over x somewhere so that it'll cancel? We sure do. 1 over x is there. So that's our strategy that's going to work here. U is log x. Take the derivative with respect to x of u, and it's the derivative with respect to x of natural log x. The derivative with respect to x of u is du dx. The derivative with respect to x of natural log x is 1 over x. My strategy requires you to solve for dx. If that's the case, x times du equals dx. That's what I'm going to substitute. So when the time comes, we're going to replace dx with x du. And notice that'll be nice because it'll knock out the x in the denominator. The top is going to be u. And then the last thing I have to substitute is the endpoints. So currently I have x equals 1 to x equals e. I like to write it that way for emphasis. Now if x equals 1, what is u? U is natural log 1, which is 0. If x equals e, what is u? Natural log e, which is 1. So rewriting this, natural log x is u, x stays x, dx of course is x du. And now we could work on our endpoints. Again, log 1 is 0 and log e is 1. And the x's cancel. What are we left with? Integral as u goes from 0 to 1 of u du. Well, that's pretty easy. The antiderivative of u is u squared over 2. Then we're going to evaluate that as u ranges from 0 to 1. Plugging in 1, we get 1 squared over 2. Plugging in 0, we get 0 squared over 2. Subtracting those, and our answer is 1/2. Our next question is the integral from 0 to pi over 6 of sine 3x over 1 plus cos 3x squared. Now the derivative of sine 3x is 3 cos 3x, which I kind of see, but I don't see 1 plus cos 3x. The derivative of 1 plus cos 3x is going to be negative sine 3x times 3, and I have a multiple of that upstairs. So that's our indicator to determine what u is going to be. So we're going to use a u of 1 plus cos 3x here. The derivative with respect to x of u is the derivative with respect to x of 1 plus cos 3x. Du dx is what? Now the derivative of 1 is just 0. The derivative of cos of something minus the sine of something times the derivative of the something, using the chain rule. So the derivative of cos 3x is minus sine 3x times 3. Again, left-hand side du dx, right-hand side negative sine 3x times 3. So we're going to say then du dx is negative 3 times the sine of 3x, and I want to solve for dx. I want to substitute for that dx. Multiply both sides by dx, so we're going to say du equals negative 3 sine 3x dx. To solve for dx, we're going to divide out the negative 3 sine 3x. And we have du over negative 3 sine 3x equals dx. That substitutes for dx. 1 plus cos 3x will be u, so the bottom is going to be u squared. We're going to leave the top alone. Sine 3x is still sine 3x. You can see it's going to cancel. nicely when we substitute the dx, but I still have to change the endpoints. So for emphasis, I'm going to write x goes from 0 to x goes to pi over 6, and we need to change those to u's. So if u is cosine of 3x, if I plug in 0, I get u is 1 plus cos 3x. Plugging in 0, I get 1 plus cos 3 times 0. But cos 3 times 0 is 0. Cos of 0 is 1. 1 plus 1 is 2. So my lower endpoint will be u equals 2. How about my upper endpoint? Well, if x is pi over 6, u is 1 plus cos 3x. 1 plus cos 3 times pi over 6. 3 times pi over 6 is pi over 2. This will become 1 plus cosine of pi over 2. Well, cosine of pi over 2 is 0. Think of your unit circle. Pi over 2 is 90 degrees. There is no x value, 90 degrees, on the unit circle. Cosine is the x value. Cosine of pi over 2 is 0. So my upper endpoint is 1, which is a little strange. My lower endpoint is 2. My upper endpoint is 1. Normally speaking, we prefer to have the lower number on the bottom. But this is what we have. Here's u. Lower endpoint is 2. Upper endpoint is 1. And here is what I'm going to substitute for dx. So let's see this. Lower endpoint is 2. Upper endpoint is 1. Sine 3x stays upstairs. Bottom is u squared. And then du over negative 3 sine 3x is what we have for dx here. And you'll notice the sine 3x's go away. So we have 1 over u squared du over negative 3. This, of course, is 1 over negative 3. Negative 1/3 comes out in front. So we get negative 1/3 times the integral as u goes from 2 to 1 of 1 over u squared. But as I mentioned, we're not real happy that the larger number is on the bottom. But we can switch the order of these endpoints. But if we do that, we have to multiply by a negative 1. So I'm going to do that. We'll take the integral as u goes from 1 to 2. Multiplying by negative 1, that becomes 1/3. Now this is relatively easy to finish, but we're going to rewrite this 1 over u squared as u to the negative 2. And then remember the power rule. Integral of x to the n is x to the n plus 1 over n plus 1. Negative 2 plus 1, u to the negative 1 over negative 2 plus 1 over negative 1. So indeed, 1/3 u to the negative 1 over negative 1 evaluated as u goes from 1 to 2. We'll pull this negative 1 out. 1/3 times negative 1 is negative 1/3. So it'll be negative 1/3. And u to the negative 1, of course, means 1 over u, evaluated as u goes from 1 to 2. So plugging in 2, we'll have 1/2 minus plugging in 1, 1 over 1, with a negative 1/3 out front. And 1/2 minus 1 is negative 1/2. Negative 1/3 times negative 1/2 equals 1/6. And that will conclude this lesson.